Good afternoon. The first topic I will present today is the angle function for a unit speed plane curve. So let gamma define on I with values in R2 a unit speed plane curve. By hypothesis, the length of the vector Vt defined as gamma prime t is equal to 1 for all t in I. Suppose that the trace of the curve gamma is, for example, this one, and suppose also that at t equal t1, vt1 points this way, at t equal t2, vt2 points this way, and at t equal t3, vt3 points this way. What happens now if I draw these three vectors translating them in order to have their tail at the origin of the plane. So Vt1 will be a vector pointing in this direction, Vt2 will be a vector pointing into this direction, and Vt3 will be a vector pointing in this direction here. So precisely what happens is that the map which associates to t the vector v of t can be seen as a sort of path on the unit circle. S1. So this suggests the existence of a function theta defined on I with values in R such that v of t is equal to cosinus of theta t sinus of theta t. Now, more precisely, we can prove the following proposition. which says that if gamma defined on I with values in R2 is a unit speed planar curve, then there exists a smooth function whose name is angle function theta defined on I with values in R, such that Vt equal cosinus of theta t sinus of theta t for all t in I, and this function is unique up to adding an integer multiple of 2 pi. Before proving this proposition, I would like to say something about the local existence of a function theta, which makes this identity true. For example, suppose that Vt is a vector of components Vxt with Yt, and no, let's write if V x positive, then we could define such a function writing theta t equal to arc sinus of Vyt. The problem with this definition is that this is not globally defined function. Why? Because the range of this function is not maybe equal to the entire interval I. We could continue and observe that if, for example, Vy is positive, then we could choose theta t to be equal to arc cosinus of Vxt. Also in this case, we don't get a globally defined function, but only a locally defined function. So the main issue with the proof of this proposition is that we want to define a function on the entire interval I. In order to understand the idea of the proof, I would like to make a simple computation which helps us to understand the definition of angle function I will give during the proof. So suppose that this identity holds true, then what happens if I differentiate? So let's call this equation star. So by differentiation, we get that the derivative of v, that is at, it is equal to, by chain rule, to theta prime t times minus sinus of theta prime, theta t, comma cosinus of theta t. But what is this vector function here? Let's continue 2 lines below. If v of t is equal to cosinus theta t sinus theta t, then this is the function theta prime t r90 v of t. But the equation (1.9) says that a of t is also equal to the sine curvature function times r90 vt. So if we compare this equation here with this one, we get that the derivative of theta is kst. Okay, so now the idea of the proof consists in defining the angle function theta by integrating ks and adding a constant. So choose t0 in I and theta 0 in R, such that Vt0 is a cosinus of theta 0 sinus of theta 0. Okay, now the candidate global angle function as announced a few moments ago is obtained by integration of ks. So I will write integral from t0 to t ksu du, and I need to add a constant theta 0 in order to have theta t0 exactly equal to this angle here. So what is the constant I have to add is exactly theta 0. I repeat one more time. Why? Because I know that for t equal t0, the good value of the variable theta is theta 0. Okay, now we have to prove that this function is globally defined, so this means is defined on the entire interval I. In order to do that, we use a technique you learn in the course of topology. Precisely, let's define I hat contained in I to be the set where Vt equal cosinus theta t sinus theta t holds true, and we have to show that I hat coincide with I. Okay, first of all, we observe that I hat is non-empty. Why? Because T0 belongs to I hat. According to my definition of theta t, if t is T0, then I get that theta T0 is theta 0, and I chose T0 to be the time for which Vt0 is cosinus of theta 0 times sinus of theta 0. So this identity holds true for t equal to 0. Now, in order to prove that I hat is equal to I, we will show that I hat is both open and closed in I. Since I is connected, then I hat and I must coincide. Okay, let's start by the proof of the openness. So claim I at contains every subinterval of I containing T0 on which a local angle function exists. Why this is true? This is true because we can add multiple to pi so that the local and the global angle function coincides. But since their derivatives coincide, then these two functions agree on the entire subinterval. And this is the proof of the claim. So I at contains every subinterval y containing T0 on which a local angle function exists. So this says that there exists a neighborhood of T0 in I which lies in I hat. The same idea can be used for proving, okay, let's write here, that every element of I hat is a neighbor in I, which lies in I hat. So this says that I hat is open in I, of course. Now, how to prove that I hat is closed? Very simple. Suppose that V Tn equal cosinus of theta Tn no, let's write theta n sinus theta Tn holds true with Tn in I hat and limit of ns tends to plus infinity of Tn equal T bar in I. So what I'm doing here is that I'm considering a sequence of points converging to a sequence of point Tn in I hat converging to T bar. I have to prove that T bar belongs to I hat. This would prove that I hat is closed. But why T bar belongs to I hat? This is true because by continuity of the function Vt and theta t. So this is continuous because by assumption a curve is a smooth function, and theta t is continuous because it's defined by an integral. Then, no, without then, so let's erase this part. Let's write it holds true that we can take the limit as n tends to infinity of this identity here, we get V T bar equal cosinus of theta t bar e sinus theta t bar. So if n tends to infinity, this identity tends to this one. And this means that t bar belongs to I hat, then I hat is then closed because it contains its, okay, let's say it contains the limit of sequences of sequences of its element. Maybe I should write here convergent sequences of its elements. Okay, now we have proved that theta t is globally defined, and it remains to prove the uniqueness. So show that theta t is unique. How to do this? Very easy. Suppose there exists another angle function theta defined on I with values in R, then theta t and capital theta t must differ by a multiple of 2 pi. Sorry, at t0. Then since theta prime is ks and capital theta prime is ks, so in other terms these two functions have the same derivative, then they must differ by a multiple of 2 pi on I. Why? Because theta minus capital theta prime is 0. So this means theta minus capital theta is constant on I. And this constant is exactly this multiple of 2 pi. Okay, last definition that I will give, which is connected with the angle function, is definition of rotation index. So definition of rotation index. The rotation index of a unit speed plane curve gamma defined on an interval of the form AB with values in R2 is 1 over 2 pi times theta B minus theta A, where of course theta is the angle function the rotation index of a excuse me, I forgot to write that the curve must be closed. So the rotation index of a regular closed plane curve. By this I mean a curve which is not unit speed, means the rotation index of a orientation preserving reparametrization, sorry, not unit speed, reparametrization of it. So this definition says two things. It provides you the formula for the rotation index for a unit speed closed plane curve, and it says what is the rotation index for a regular closed plane curve which is not unit speed. In this case, the rotation index is the rotation index of the unit speed closed plane curve that you get by considering a orientation preserving reparameterization of this curve. Okay, some examples. So if we have a curve whose trace is this, then the rotation index is 0. Why? Because suppose that this is the point, suppose that this is the point theta A equal, gamma A equal gamma B, then if t increases, the function theta t increases up to reaching the values 2 pi when gamma t travels along this first loop, and then it decreases while gamma t travels along this second loop, and this is why from the formula of rotation index we get 0. The rotation index of a curve whose trace is this. Is instead -1. Why? Because if t increases, then the function theta t decreases, because we are moving, in this case, the function theta t is decreasing. We are moving clockwise along the curve, and the formula will give you -1, and the rotation index of a curve like this is instead equal to 3. Why? Because in this case the function theta t is increasing, we are moving counterclockwise along the curve, and there are 3 loops, so each loop gives a contribution equal to 2 pi. Okay, the next topic of today is the study of space curves, or in other terms, curves with values in R3. In order to study space curves, it's convenient to review the notion of cross product, so I give the following definition. if A equal to A1, A2, A3, and B equal B1, B2, B3 are vectors of R3, then the cross product A cross B is a vector whose components are A2 B3 minus A3 B2, A3 B1 minus A1 B3, A1 B2 minus B2 A1, and the cross product satisfies the following properties. One, A cross product B is orthogonal to both A and B. Two, the length of the cross product of A and B is the length of A times the length of B times sinus of theta, and this is also equal to the square root of square of length of A squared the length of B minus the inner product of A and B squared, and this is the area of the parallelogram spanned by A and B, and here theta is the angle between A and B, of course. The third property says that the direction of the cross product of A and B is given by the right hand rule. So in other terms, if the index gives the direction of A and the medium finger gives the direction of B, then A cross product B points like shown by the thumb. Other algebraic properties are the following ones. So A cross B is equal to negative B cross A. So in other terms, the cross product is not commutative. 5. lambda A plus mu B cross C, this is equal to lambda A cross C plus mu B cross C. Six A cross product lambda B plus mu C, this is equal to lambda A cross product B plus mu A cross product C, where lambda mu are real numbers. Another property I want to show, and which involves also curves, is the one described in lemma 1.45. So if gamma beta are space curves, that is curves with values in R3, then the derivative of gamma t cross beta t, this is given by gamma prime t cross beta t plus gamma t cross beta prime t. The cross product allows us to write down a nice formula for the curvature of a space curve. So this is the content of proposition 1.46, which says that if gamma is a regular space curve, then the curvature is given by the length of the cross product of the velocity vector with the acceleration vector divided by the length at the third power of the velocity vector. Okay, the proof of this result, it is not difficult. Let's start by making a picture. Assume that this is V of t and this is A of t. By definition of curvature, we have that K of t is okay, let's drop the dependence on time because we don't need it. So I just write K is the orthogonal component of A divided by the square of the length of V. So the orthogonal component of A is this vector. How can I find A orthogonal T in terms of V and A. Very easy. Suppose that theta is the angle between A and V, then the length of A orthogonal is equal to length of A times sinus of theta. So I write it here, and I have A times sinus of theta divided by the square of the length of V. Now I use a trick we used already in the past, so I multiply and I divide by the length of V, and I get length of A times length of V sinus of theta divided by the cube of length of V. And now I use one of the identities I showed you a few minutes before, which says that this is the length of the cross product of A and V, and this allows me to write A cross V, V cross A divided by the length of V cube. So this is the end of the proof of this result. Okay, so when we studied curves, we introduced an orthonormal basis, precisely the orthonormal basis of the osculating plane. It consists of the vectors t and n, that is the unit tangent vector and the unit normal vector. What we will do today is to complete this basis in order to get an orthonormal basis of R3, which consists of three vectors of unit length which have a geometric interpretation. So I will give the following definition. So let I be a regular space curve let T in I a point where the curvature is non-zero, then the Frenet frame at T is the basis T of T, N of T, B of T over 3, defined by the following formulas. The tangent vector is V of T over its length. The unit normal vector is A orthogonal of T divided by its length, but this is also equal to T prime T divided by its length. And the last vector, which is a new one, is defined as a cross product of T and N. And this vector is called unit binormal vector at time t. Okay, let's try to make a picture. So suppose that this is the curve, this is a trace of the curve gamma, this is T, this is N, in yellow you have the osculating plane, and the new vector B points upward, like this, for example. So BT is always orthogonal to TT and T. This implies it is orthogonal to the osculating plane. Why? Because B has been defined as the cross product of T and N. And as a consequence, B prime T measures the rate of change, let's say how the position of the osculating plane changes. The next important definition I want to introduce is definition of torsion. The torsion will be a scalar function which provides the rate of change of the position of the osculating plane. Okay, let's erase this picture. One idea for defining for possible candidate to the torsion function could be the following: to write tau equal the length of B prime. This is not a good idea for two reasons. The first one is that this definition let's say this function would depend on the parameterization. I don't show this in detail. And second problem, we would like to have, if possible, we would like to have a sine function that is a function which can have which can take positive values and negative values. Let me check how much time I have. Okay. The good definition is the following. Is definition 1.48, which says that let t in I with kt different from 0, then the torsion of gamma at time t, denoted by tau t, is given by minus the inner product of b prime t with the normal vector n of t and divided by the length of the velocity vector. Okay, let's try to understand why this definition. Okay, we have to find B as T cross product and T. Okay, so what about now B prime? B prime of T is orthogonal to bt. This is easy to see. Why? Because you can differentiate this inner product, which is always equal to 1. Why? Because this is the length of bt square and this is 1. So this is 0, but this is also equal to twice b prime t multiplied by bt. So b prime t multiplied by bt is equal to 0. This says b prime t is orthogonal to bt. Now let's prove that b prime t is also orthogonal to t of t. So we have to show that b prime t t, this is 0. Okay, first of all, we observe that this can be written as minus t prime t pt. Why? Because we can differentiate this inner product, which is equal to 0, because by definition of b is orthogonal to t. So this is equal to b prime t tt plus b t t prime t. So if the sum of these two numbers, these two functions is 0, then this is true. We proved that according to equation 1.7, we have that n can be written as t prime t over length of t prime t. So we can replace t prime t by n t multiplied by the length of t prime t. So this is equal, I will write here, to negative inner product of length of t prime times n multiplied by, I forgot to write the dependence on t, so let's write properly, t prime t and not t bt and this is equal to negative length of T prime multiplied by the inner product of NT with BT. But this is 0 because N of T and B of T are orthogonal by definition of B of T. So B prime T is orthogonal to T of T and to B of T. This means that B prime of T is parallel to N of T. So if B prime is parallel to N of T, then the length of B prime coincides with the inner product and N. So this explains why the numerator of the definition I gave you before is B prime T N of T. Now it remains to explain why I divided by V of T. The reason for this is that as lemma 1.48 says, the torsion is independent of the parameterization. Okay, I think I should stop here. We will prove this result next time. So that's all for today. Thank you for your attention.